We're going to take a look at our exponential equations and graphs review for a test. I'm going to have some videos posted on how we will do some of the calculator stuff. You'll hear me refer to a calculator, but I have these already pre-done, so we'll just refer to the answers. If you have a question on how the calculator is to be answered, you can click on a video. I'll try to put it in the home screen. All right, first of all, we've got to refer to our formulas. We're either going to use the continuous compounding that involves the e, or we're just going to use one of our compounding interests. Just keep an eye open for that word, continuous. So it says a deposit of $270 is made to a checking account that pays 3% annual interest compounded quarterly, and that's a key word right there, compounded quarterly. Okay, so if we have this amount, remember we always start with our investment in front, 270. We're going to multiply that times 1 plus or minus the rate depending on what if it's a depreciation or an appreciation. And this is going up, so this is a plus sign. We are getting 3% interest, but we are getting it quarterly. So we're not going to get the full 3 at the end of the year. We're going to get the 3% divided 4 ways. So we'll take our 3% and divide by 4. And since we are dividing it into 4 times, we're going to get 4 times as many occurrences. So when we're writing an equation for this, and x being time, whichever way you want to put it, write an equation that fits this scenario, that would be the equation that fits this scenario. Remember, the n values are going to always pop up in the denominator and then in the exponent with the variable. And then it says, how much will this be worth after 5 years? Well, in this case, all we would do is substitute in the number 5 for x. Like I said, I've already done some of these things in the calculator, so I'm just going to put the result. And the result would be $313. And since we are talking about money, we would round to the hundredths place, so this rounds up to 52 cents. Letter B, it says the value, a vehicle purchased for $12,000 will depreciate. It will decrease. So we have $12,000. And since the value is decreasing, we are going to take that amount away from 1, because the 1 stands for 100%. And it says the depreciation will decrease by a rate of 8% compounded weekly. Well, we have 52 weeks in the year, so our denominator and then our exponent is going to be 52. So we would divide by 52, and then we would put a 52 into our exponent, and then we would add our variable x or t, depending on which one you choose to use. So our equation for this scenario would be this. Now, later it asks us, when will this be below $5,000? I personally went to a table and created a table from my calculator, and 0 was 12,000. 1, after 1 year, that was $11,076.71. And I just kept going until I got below the number 5,000. And the first time that happened was actually in year 11. Year 11 says $4,974.02. So the answer, how many years until it's worth less than $5,000? That would happen 11 years later. All right, it says next, a $1,000 government bond is purchased. You will receive 2% annual interests compounded monthly. So our starting amount is going to be the $1,000. So we have $1,000. And since this is increasing in value, we will have a plus sign. It is 2% annual, so that will be the percentage that goes in the top. Compounded monthly, 12 months in a year, so that value is 12, and so is the exponent. I'm going to use a t here just to change it up. So this would be our scenario. And this one asks how much time, or excuse me, how much is it worth after 30 years? So all we need to do in this case is to take the 30 years and substitute it in for the t, the time. And when we plug that in, we get the number 1,821.21. It's actually 28.208, but the 8 rounds up to a 1. So this would be our value after 30 years. And that's a reasonable number. 2% is not a very high percentage, but 30 years is a long time. So our value is almost doubled after about 2 years. Now this one's a little bit of a tricky one. We're talking about a tree. It's currently 0.12 inches tall. It grows at an annual rate of 150% compounded continuously. Well, compounded continuously is where we're going to use our PERT formula, which is principal times the natural base to the rate times time power. But in this, we have to also pay attention at the end, because look what we're looking for. It says, how long until the tree is 3 feet tall? Emphasis on the word feet. We're actually comparing two different things here. We're comparing inches to feet. So what I like to do personally is I like to get rid of the transition right away. So what I'm going to do is convert 0.14 inches into feet. Well, since there are 12 inches in a foot, I will have to divide this by 12 to figure out how long that 0.14 inches is in feet. And what I learn is that is 0.0116 repeated. And the alternative to that is to actually put this amount in for our formula as our starting amount. So let's take a look and see what that looks like. So we're going to go to the starting amount. Well, the starting amount is the 0.14 inches, but divided amongst 12 because we're trying to figure out the feet. We can leave it that way as a starting amount as well. Since this is compounded continuously, we will use the E. Our rate in this case is higher than 100%, so it's going to be 1.5. And then on this case, we're not looking for a period of time. What we're looking for is when a value reaches 3 feet. And we've already converted it to feet, so we're good here. So I can plug this value in just like this, and then all I've got to do is look through my table and decide where this value gets higher than 3 feet. If you didn't convert it at the beginning, you will have to convert it at the end. So here's what I'm looking at. After year one for full year, we're at 0.05. Year 2, 0.23. Year 3, we finally get over a foot, 1.05. And then year 4 is at 4.7. And it does ask when it will be taller than. When it will be taller than 3 feet. So that when it will be taller than 3 feet is any year past the 4th year. We don't have a plug-in value like many of our other ones. In this one, we have to refer to a table. Good news is later we'll learn some logarithms and learn how to solve. But until then, we can go to our calculator, look through our table, and just see what we have. All right, let's take a look at these. These next two can be a little confusing, so let's see what we can put together here. So it says find the equivalent annual rate of interest 3% compounded monthly. So we talked about this before. How much are we actually getting? Yes, we're going to get 3%. That's what the annual rate is, but when we compound it, we actually get a little bit more. We actually don't have a principal amount, but we don't need one here. We will just use that formula that we have been using, which is the 1. In this case, it's plus 0.03. And we're trying to compound monthly, so we would divide this by 12. And then it would be to a 12x power. And the reason for this is whatever the amount is, it's a percentage. So the principal doesn't matter. The higher the number, the higher it'll incur, but it's still going to have the same rate. So the 0.03, we're getting 3% every year, but it's divided monthly, so we're going to only get 0.0025% each month. When you multiply that number by 12, what you'll learn is that that number 12 times will get us back to our 3%. So you're still getting 3% annually, it's just it's divided 12 ways into the 12 months. So we can convert this thing now by rewriting this as 1.0025 to the 12th power, because those are all numbers. The variable, we're kind of out of luck, to be honest with you. We can't calculate a variable because it's an unknown amount, but we can calculate those values that are numbers. And if I hit that in my calculator and I go 0.0025 to the 12th power, what I end up with is 0.0304. So you see, I'm actually getting a little bit higher than 3% interest. What I'm getting is a value of 3.04%, because what we have to do is move that decimal place over 2 times, 1, 2, and then we are sitting at our percent. It's not a whole lot, but it's free money on that case. Now the next one's a bit of a typo, I believe, because it says find the equivalent monthly rate for interest compounded 5%. If that were truly the question here, all we would have to do is take the 5% and divide by 12, because that's the equivalent monthly rate. But I think what this is talking about is finding the annual return actually if we have a monthly rate. So it's going to be just like the other one. 1 plus the 0.05 divided by 12. And this is monthly, so it would be 2A 12T. So we would have 1 plus that 0.05 divided by 2. And again, if that's truly what the question is, what we have here is that is our monthly rate. We're paying the, whoops, let me put my decimal, 0.0042 each month. So this would be 12T. And we are going to do the same as the last one. We are going to take that we're going to add the 0.0 first to the 1. So what we end up with is 1.0042. And we're going to move the 12th power down to those, because numbers will interact with other numbers, but the variable will not. And what we learn is 1.00416.2 becomes 1.051. So the decimal place, after being moved over 2 times, will put us at 105.1%. So if it's 105.1%, that means that we are getting 5.1%. Next thing we're going to look at, number 2, is we're going to start introducing our transformations. Question 2 says, f of x is the parent function of g of x. What is f of x? Well, this is a real easy one. The parent function is always going to be determined based on what the exponent is attached to. So since this is attached to a 3, it comes from the parent function, the triple family. So the parent function is going to be 3 to the x power. Nothing else matters on this. The transformations will change domains. They won't change domains, excuse me. They'll change ranges and steepness, but they will not change the parent function. So whatever it's attached to, it is. So even in like number 3, it says list the transformations. Well, we don't need to list to state this, because whatever the 2 was, it is there. But that's just there to remind you. So let's list our transformations, remembering on our transformations that the 2 does not represent a transformation. The 2 only represents the family of the functions we're in. So this is a doubling family. So let's talk about this. There is understood parentheses There's understood parentheses around the exponent. So anything happening there is horizontal, anything else is vertical. So let's take care of the horizontal right off the bat. It is horizontal because it is in the parentheses. It is a horizontal shift because it's a plus or a minus sign. And remember, with horizontal, there are always tricks. So this feels like I should be going left 1 because of the minus sign, but we're actually going to go horizontal shift right 1 unit. Next, we'll look at the value in the back. We'll save the toughest stuff for last in this case. Well, this is outside of the parentheses, which makes it vertical. It's going to shift it up or down depending on the sign. It is a vertical shift because it is a plus sign. And we do exactly what they say. Plus seems like it would be up, and on verticals it is. It does exactly what you would think. And then the last thing is actually 2 things. It feels like that should be a vertical stretch by a factor of -3, but remember, vertical stretches can never be negative. That's a different transformation in itself. So we have a vertical stretch by a factor of 3. And we have a 4th transformation in this case, which is a vertical reflection. You could also call this a reflection across the x-axis. Both of those things are stating the same thing. Number 4, family is base 10. That has nothing to do with transformation, all to do with family. So let's start with the easy one on this case. Well, there's a subtracting directly at the back, so we have a vertical, and it is subtraction because which makes it a shift. And since it is vertical, we do exactly what it feels like, which is down 4. Next thing we'll look at, we'll take care of the horizontal transformation, which is the understood parentheses. So we have a horizontal. It is also a shift because it is a plus or minus sign. But in this case, it feels like we should be going left 3, but horizontal always have the reverse behavior. So it's actually going to go right 3. And then the last one, the 1/2 that's in front here, is vertical because it's outside of a parentheses, so we know that much. It's multiplication, which makes it a stretch, but in this case it actually makes